Chapter 2 of the Fast Micro tutorial involves setting up your own analysis. This chapter will guide you through the process of setting up a study folder for performing consequence calculations. The tutorial supplies all of the input values that we need to complete the analysis.
First thing we need to do is create a new study folder. To do this, go to File, New. The program will close the Fast example study and open a new study folder named New Fast Micro. The new study folder is not empty but contains global weather folder, which contains 3 different weather types, the same as those in the Fast example study. You cannot save the study folder with the name untitled and save it with a real name immediately. Go to File, Save As, create a folder with your name and save it as Tutorials. We've now set up the map data. To set up the map data, go to the Map tab and ensure that there is a raster image set. If there is not a raster image set, go to the New Fast Micro and insert a raster image set. To insert a raster image, select the set and then insert a raster image. Go to Browse and then inside the System C, Program Files, DMVS, the fast build that you're using, examples, and then Maps folder. There's a tutorial.tif folder. And then OK the dialog. When you click on OK in the Place dialog, a dialog called the Coordinate System wizard will open. This is the first step in selecting a coordinate system for the analysis. It is only essential to select a system if the placement mode is set to georeferenced or to by header, or if you want to use GIS database in the analysis. When you're using interactive placement mode and will not be connecting to the GIS database, which is the situation in this tutorial, you can click on Default in the wizard dialog and leave the coordinate system undefined. The wizard dialog contains a help button, and this gives you a quick way of viewing the overview of the user and definition of coordinate systems in Fast Micro. When you click on Default in the wizard dialog, there will be brief pause and the map window will then open to the right of the study tree pane. The cursor will be in the form of a crosshair and you must drag and drop to place the image in the window. This sets the initial value for the map coordinate for the image, which you will set to the correct value in the next step. You now need to set the coordinates and the size of the image. Double click on the tutorial icon to open the input dialog. Go to the Geometry tab, set the eastern coordinate to 196855, set the north coordinate to 436053, set the width to 4489 and the length to 3570. Leaving the rotation at 0 degrees. OK this dialog. When you click on OK, the image will probably disappear from the map window because it has moved to a location beyond the scope of the window. Select Fit All from the map menu. And the map window will change to display the image covered by the image. The coordinate values for the image will be in the national coordinate system for the country, and the values for the area covered by the map are 6-digit numbers. By default, input dialogs display only 4 significant figures of any number that you are editing, and with this setting you will find it difficult to be sure that you have entered the coordinates. To change the setting for number of significant figures, select Preferences General from the Options menu. Go to the Miscellaneous tab and change the number of significant figures from 4 to 6 and OK this dialog. We will now define the first model for a toxic rupture. In the tutorial study folder, move to the Models tab section. The first model you will define represents the rupture of a vessel containing a toxic material, which is one of several models dealing with a toxic material. Select the study icon and then select Folder from the Insert menu and rename the inserted folder Toxic, which is where you will place all the models that represent toxic releases in this folder. Turn on the option to insert model on the map. In the Options menu, select the option to insert models on map. By default, this option is turned off, and when you insert a model, the icon will appear immediately in the study tree. If you turn the option on, then the model icon will not appear in the study tree until you have clicked on the map to set the location for the model. In this tutorial, you will insert the models on the map in approximately the correct location, and then the correct location is necessary in the input dialog. So now you insert a vessel pipe source model. So select the toxic folder, then select vessel pipe source in the insert menu. The map window will open if it is not already open, and the cursor will turn to a crosshair. And you should click at a point near the centre of the site to place the model. After you've clicked, an icon will be added to the study tree and a dot will appear in the map to show the location of the model. Rename the icon CL2 Rupture. CL2 Rupture will have a red border around it, showing that it does not have a full set of input data. You will not be able to run the constants calculations for the model until you have supplied values for all the mandatory fields, as this will be described below. Setting the input data. Double click on the icon for the model to open the input dialog. All of the fields in the first tab section are blank, and those that are enabled have red borders. A field with a red border is a mandatory field. You must supply a value for such field, and you will not be able to run the calculations for a model that have any mandatory fields unset. On the Materials tab section, to set the discharge material, click on the button with the three dots to the right of the discharge field, and then select chlorine from the list that appears. The vessel is a sphere with a volume of 120 meters cubed. This model will represent the vessel with a maximum degree of filling, which is 85%. Select volume as the method for specifying the inventory and enter a value of 102 meters cubed. Chlorine is held under saturated conditions at atmospheric temperature. Temperature will vary depending on the season and time of day, but for this model, a value of 10 degrees C will be used as representative. To set these process conditions, choose saturated liquid from the first drop-down list and temperature from the second drop-down list, and set the temperature to 10 degrees C as shown. When you move the cursor away from the temperature field, the program will calculate the saturated pressure for that temperature and display it in the pressure field. To define the process conditions for a material that is not held under saturated conditions, you must select both temperature and pressure from the list and give both values. On the Scenarios tab, you specify the type of hazardous event that you want to model. The range of types available will depend on the process conditions you have specified. There is only one scenario type available for modelling the rupture of a pressurised vessel. This is catastrophic rupture, which is selected by default. The other scenarios are either longer duration releases or applicable only to insulated tanks. The other fields in the tab section are not relevant to this rupture scenario. You can take the default settings for all the fields in this tab section. In the Pipe tab section, all the fields are disabled when the scenario is set to rupture. They are relevant only to line rupture, disc rupture and relief valve scenarios. The Vessel tab section is disabled when the scenario is set to rupture. For all of the other scenarios, some of the fields in the tab section will be enabled, with the combination depending on the scenario that you have chosen. On the Location tab section, the elevation has a default of 1 meter, taken from the system parameters, but you should set this to 7.37 meters, which is the elevation of the centre of the sphere above the ground. The program requires a criterion for stopping the dispersion calculations, either a maximum distance or a minimum concentration. For this tutorial, set the concentration of interest to 100 ppm. After you have set this concentration and moved the cursor to a different field, The user average time below the concentration will acquire a red border, which shows that it is mandatory. You must specify the averaging time to be used in the calculation for stopping the dispersion. For a toxic release, the list allows you to choose the toxic averaging time or the time associated with the ERPG, IDLH or STEL measured of toxicity, or to specify a user-defined time. For this release, select the toxic option, which is set in the toxic parameters and has a default value of 600 seconds. The location tab section allows you to select additional averaging time for which you want concentration values. If you make any selection in the final section of the tab, the results will appear in the averaging time report, as you saw in the previous chapter. In the geometry tab section, set the eastern coordinate to 198,492 and the northern coordinate to 435,063. In the bund data tab, if there is a bund around the vessel and you want to take this into account in the modelling of pool spreading and evaporation, you can check the bund exists option and enter a description of the bund. For this sphere there is no bund, so you can leave the tab section with the default values. On the indoor-outdoor tab section, all of the fields are disabled in the scenarios catastrophic rupture outdoors. Some of the fields are enabled for longer duration scenarios, as you will see later. In the Flammable tab section, the fields are disabled when the material is toxic only. For a flammable release, they allow you to choose between two models for jet fires. The Toxic Parameters tab is used in modelling the build-up of toxic concentration inside a building and the exposure of a person inside the building. By default, these calculations are set to unselected, but for this tutorial you should change them to selected. The calculations require information about the ventilation rate for the building and about how long people remain in the building after the cloud has passed. The concentration is lower outdoors than indoors. By default, these values will be taken from the Toxic Parameter tab section for the model, but if you choose wind speed dependence for the ventilation specification, then the values will be taken from the data for the weather, which means that the values may be different for each weather. For this tutorial, leave the ventilation specification with the default values of case specified, and take the default values for the building exchange rate and the tail time. The input process involves examining a large number of input fields, but the number of values that you have to enter in order to complete the data for this model is small. Once you've completed all the data, click OK. We will now run the calculations and view the results. Select the model and select Run Model from either the Run menu or the toolbar. When the calculations are complete, view the graphs for all the weathers. You will see that there is no pool vaporization tab in the graph window, which means that the liquid in the release did not rain out. If you want more information about behaviour of liquid droplets in clouds, you should view either the commentary report or the dispersion report. The central line concentration graph will appear to show a concentration of 0 at all distances downwind, but this is because the default scale on the concentration axis goes up to 1 million ppm. To see the concentration levels for this release, you must set the scale yourself. Select Scale and Labels from the right-click menu, or the graph menu to open the Scale dialog. Then uncheck the automatic scaling option and set the maximum concentration to 1000 ppm. OK the dialog. With the changed scale, you will be able to see the different concentration profiles for the different weather conditions. The concentration graphs only ever show the outdoor concentration, but if you move to the Toxic tab, you will see that the probit lethality and dose graph display separate results for indoor and outdoor effects. and that there is separate footprint graphs for outdoor and indoor effects. The lethality graphs shows that the greatest downwind effect distance is for the f1.5 meter per second weather outdoors, with a distance of about 2.5 kilometers to a lethality level of 10%. The indoor effect for this weather reaches about 2.25 kilometers to 10% lethality. The shortest downwind effect distances are for the d5 meter per second indoor, which reaches about 1.4 kilometers for a lethality level of 10%. We will now define a second release, a toxic liquid from Pipework. Copy the first model into the same folder and rename the model CL2 liquid pipework. Much of the input data for the vessel rupture is also applicable to the pipework failure, so you can use copy and paste from the edit menu. Open the input dialog for the CL2 liquid pipework. On the materials tab section, you should leave this tab section with the same values as for the rupture, since the material and the process conditions are the same as for the rupture. On the scenario tab section, set the scenario type to line rupture and the phase to be released to liquid. The line rupture scenario models the full bore rupture of pipework attached to a vessel, and the discharge calculations take into account the effect of friction in the flow from the vessel to the point of rupture. To model a release from the body of the vessel with no frictional loss in discharge, you would choose the leak scenario. When the vessel contains saturated liquid, you will be offered a choice of release phase from the line rupture scenario: a vapour release from the top of the vessel or a liquid release from the bottom of the vessel. The list of phases include two phase, but this is only enabled for the disc rupture and relief valve scenario for modelling over filling of the vessel. On the pipe tab section, the pipe length is the length of pipework between the vessel and the point of rupture, and you should set it to 9 meters. To set the internal diameter to 1 inch, click on the millimeter to the right of the field and change it to inch. You can then enter the diameter directly in inches rather than having to perform the conversion yourself into the default units in millimeters. Set this internal diameter to 1 inch. Leave the pipe roughness with the default values taken from the system parameter. The number of valves is used in modelling of frictional losses, and you can leave them as 0. The other fields in the tab section are not relevant to Fast Micro and will always be disabled. On the Vessel tab section, set the liquid head to 4.6 meters. The other fields in this tab section are not relevant to Fast Micro. On the Location tab section, set the elevation to 0.1 meters. With this setting, the liquid droplet will probably not evaporate inside the cloud, and will probably rain out and form a vaporizing pool. Leave the other fields with the same values as for the rupture. In reality, the release location would be offset by a few meters from the centre of the sphere, but this difference is insignificant compared with the effect distance from the chlorine and can be ignored. Move to the Indoor-Outdoor tab. For a continuous release scenario such as line rupture, you must specify the direction of release. Choose horizontal from the list, which is the correct setting for this type of unobstructed rupture of horizontal pipework. The list of directions includes a second horizontal option, horizontal impingement. You should select this option if the release is in congested areas and the release is likely to impinge on a wall or other equipment. The program will reduce the momentum of the release, which will reduce the amount of air mixed into the jet during the initial stage. On the Discharge Parameters tab, there is one bend in the 9 meter of pipework, so you can set the frequency of bend to 0.11 per meter. This completes the input data for this stage, and you can click on OK to close the input dialog. We will now run the consequence calculations. Select the model and select Run Model from the options from either the Run menu or the toolbar. When the calculations are complete, view the graphs for all the weathers. You will see that there is a pool vaporization tab in the graph window, which means that liquid in the release did not rain out. If you view the report and look at the commentary report, you will see that the rain out fraction is only around 0.019 for the 1.5 d meter weather. We will now run the consequence calculations and view the results. Select the model and select Run Model from the toolbar or the Run menu. Open the graph window and select all the weathers. You will see that there is a pool vaporization tab in the graph window, which means that liquid in the release did rain out. In the toxic lethality graphs, the outdoor lethality footprint shows that the F1.5 meter per second weather outdoors has the greatest distance for a lethality level of 10%. We will now create the third model, toxic vapour from Pipework model. The vapour release is a rupture of 2-inch pipe attached to the top of a sphere. The line runs 3.4 metres horizontally, then vertically downwards, and the rupture is assumed to occur 1 metre from the ground. Create the model as a copy of the liquid Pipework model. And rename this copy CL2 Vapour Pipework. Open the input dialog. On the Scenarios tab, change the phase release to Vapour. On the Pipe tab, change the pipe length to 13 metres and the interval diameter to 2 inches. On the Indoor-Outdoor tab, change direction to down, impinging on the ground. On the Location tab, change the elevation to 1 metre. And on the Discharge Parameter tab, change the frequency of bend to 0.08 per metre. And OK the dialog. The release rate from the 2-inch vapour line is similar to that from the 1-inch liquid line, and the 2 pipework releases give similar effect distances. We will now define 3 flammable releases. There's a propane sphere at the far north of the site. The propane sphere is the same dimensions as the chlorine sphere and the same design of pipework, and is also operating under saturation conditions at atmospheric temperature. And we will now set the input data for the models. You can define the rupture and the 2 pipework failures by copying the 3 toxic models and simply changing the selection of discharge material in the eastern coordinates. So to copy the models, select the toxic folder, select copy and paste it into the study, rename it to Flammable, and in the name of the model, change each name to C3. Now we need to change the material selection. Open the input dialog and click on the button with the three dots to the right of the discharge material and change the selection from chlorine to propane. The list of materials is arranged alphabetically, and you can move quickly to propane by clicking on the list and typing in P. And then OK this dialog. When you return to the Materials tab section, you will see that the program has recalculated the saturation pressure at 10 degrees C and also the mass of the inventory. You must make this change for each of the three models. You must then change the concentration of interest. When you move to the Locations tab, you will see that the toxic averaging time is no longer set for user averaging time, and that this field is now shown as unset and mandatory. The material is flammable only, so the toxic averaging time is not included in this list, and the program is prompting you to make a different selection for the calculations of the stopping concentration. For a flammable release, you would not want to calculate the concentration to a value as low as 100 ppm, since the cloud will not pose a hazard once it is diluted much below the lower flammable limit of 2% or 20,000 ppm. You could set this concentration yourself, but for a flammable release you can also leave the concentration of interest blank, as shown, and the program will automatically stop dispersion calculations once concentrations reach 50% of the LFL, as calculated with the flammable averaging time. You must make this change for each of the three models. If you move to the Jetfire tab, you'll see that there are 3 levels of radiation, and that the default setting for these 3 levels is unselected. These calculations are not selected by default because they can be time consuming, so you would normally only select them if you know that you need them for a particular analysis or particular model. For this tutorial, you will set the lethality calculations as selected, and then open the radiation level dialog. Change the settings to lethality level of 0.2 for number 3, and leave all other areas the same. You must make these settings in the Fireball tab section when you are setting the data for the Rupture model, and in the Jetfire and Pool tab sections when you are setting the data for the 2 Pipework models. Once all the input dialog is complete, we will run the consequence calculations and view the results. Select the Flammable folder and use the Run Models option to run the calculations for all 3 models. You can also view the results for all 3 models at once. Select the Flammable folder and then select View Graphs. The Plot System dialog will appear, prompting you for the weather for which you want to view the results. When you are viewing results for multiple models, you can only choose a single weather, so the weathers have radio buttons beside them, whereas they have checkboxes beside them when you are viewing results for a single model. Select the 1.5 F weather, which should give the greatest effect distance for dispersion. The graph window contains tab sections for concentration graphs, as with the toxic model, but it contains Jetfire, Fireball and Flashfire tab sections instead of the toxic tab sections. Propane releases do not produce any liquid rainout, so there are no pool fire tab sections. The Jetfire tab section contains 3 graphs which are presenting results for the 2 pipework failures. The first graph shows radiation levels versus distance. The second shows intensity radii to the lowest of the 3 radiation levels set in the parameters, and the third graph shows lethality radii to a lethality level of 1%, which is the lowest of the 5 lethality levels that you set for the model. The maximum downwind distance shown in these graphs is around 33 metres, which is the distance for 4 kilowatt per metre squared for the liquid release. There is also a dose radii and probit radii graph. The Fireable tab also contains 5 graphs, with the radii graphs showing the results for more than one level. The maximum downwind effect distance is about 560 metres to a radiation level of 4 kilowatts per metre squared, and the distance to a lethality level of 1% is about 290 metres. There is no ellipse for a lethality level of 100% because the fireball does not produce the necessary radiation dose at the height of interest. The early explosion graphs contain results only for the rupture, since immediate explosions are assumed not to occur for continuous releases. However, the late explosion graphs contain results for all 3 models. The late explosion worst case graph shows the effect radii for the explosion time, which give the greatest downwind distance for an overpressure of 0.02 bars, and the legend for the late explosion time graph gives the time at which the worst case explosion occurs. The greatest downwind effect distance is 1,100 metres for the rupture, and it occurs at 7.4 seconds. The flash fire graph shows the zone for the cloud at the time at which it covers the maximum area. For the rupture, this gives a maximum downwind effect distance of 350 metres to 10,000 ppm, whereas for the 2 pipework releases, this gives a distance of about 70 metres for the same concentration. The propane is delivered to the facility by tank wagon from a marshalling yard 10 kilometres to the north. The deliveries take place once a week, involving 2 tank wagons, and are always during the day and never at night. The wagons are 10.6 metres in length, 2.6 metres in diameter, with a volume of 54 metres cubed, raised 0.5 metres above the ground, and are delivered with a fill level of 80%. The propane is under the same conditions as in the sphere. Under saturation conditions at atmospheric temperature taken at 10 degrees C. There are many hazardous events that could be modelled for the tank wagons, including leaks during the unloading process. This tutorial will consider only the rupture of a wagon under normal operating conditions, a leak from the liquid side of a wagon, and a fireball produced by catastrophic rupture of a wagon under flame impingement. All events are assumed to occur while the wagon are in the unloading point 100 metres south of the propane sphere. We will now define the rupture of the wagon. So insert a new folder into the study and name the folder Tank Wagon. Create a copy of the rupture model from the Flammable folder. And rename this copy Wagon Rupture. Open the input dialog. Change the volume in the materials tab to 43.2. Location, change the elevation to 1.8. And in the geometry tab, change the north coordinate to 435,581. And OK the dialog. Now to define the fireball failure under flame impingement, copy the wagon rupture model into the tank wagon folder. Rename the copy Wagon Fireball and open the input dialog. On the Scenarios tab, tick the vessel burst pressure used in fireball calculation box and set the value to 8.57. The burst pressure is 60% greater than the normal operating pressure and is used in calculating the surface emissive power of the fireball. And OK this dialog. We will now define the leak from the liquid side of the wagon. Copy the rupture model into the tank wagon. And name the copy Wagon Liquid Leak. Open the dialog and on the Scenario tab, change the scenario type to leak, and the hole diameter be set to 1 inch. On the Vessel tab, set the tank head to 1.95 meters. On the Location tab, set the elevation to 0.5 meters. On the Indoor-Outdoor tab, set the direction to down, impinging on the ground, and OK the dialog. For a release from the body of a vessel rather than from attached pipework, you should set the scenario type to leak. This will give a larger discharge rate since there are no frictional losses during the flow to the leak location. For the leak scenario, you specify the leak size in the Scenario tab section. The leak is assumed to be at the top of the tank, which is the most conservative assumption from the tank head and the duration. We will now run the calculations and view the results. Run the calculations for the tank Wagon folder. And now view the graphs for the 1.5 F weather. And examine the Fireball results. The Fireball model gives slightly larger effect distances than the Rupture model, with a distance of about 500 meters to 4 kilowatt per meter squared, compared with 440 meters for the Rupture model. This shows the effect of the higher vessel pressure used in the Fireball model to model failure under flame impingement, whereas the Rupture model considers a rupture under normal operating conditions. You have now completed your tutorial, and you should save the study folder in order to save the changes you have made. By default, the program will only save the input data, which means that next time you open the study folder you will have to rerun the calculations in order to view the full results. However, if you select the Save As option from the File menu, the Save As dialog will contain an option to save results as well as your input data. If you select this option, the program will save the full set of consequence results, and you'll be able to view the results immediately the next time you open the study folder, although you should be aware that the file may be large.
This tutorial has not covered every feature of the program, but you should now have enough of an understanding of the approach and methods used in the program to be able to explore the remaining features yourself, with the assistance of the online help. If you need further detail on any aspect of the program, or if you need guidance on how to model a particular situation for your facility, you should contact product support using the details given under product support in the help menu.